Welcome! Today we are going to have a look at some revision exercises in preparation for your exam. So, question number 1. Determine whether the vectors u, v, and w span the vector space R2. So we want to start by showing that these vectors are linearly dependent. So let's say that. The vectors u, v, and w are linearly dependent. And we know that just by looking at them because we've got 3 of them in a 2-dimensional space. So they must be dependent. So let's say specifically why, since minus 5 times the first one, and you can just see this by guessing, or you can find this by solving for alpha and beta, plus 2 times the second one equals w. Okay, so now we want to choose a basis for the span of u, v, and w. Let's just choose u and w because w looks fairly simple and so does u. So notice that the vectors 1, 1 and minus 1, 1, they're not multiples of each other, so they are linearly independent. And we have span u, v, w equal to span of u and w. So u and w is a basis for the span of u, v, and w. Okay, so now that we have that, so to show that span of u and w is equal to R2, first note that any linear combination of u and w is an element of R2. So span, which is the set of all linear combinations of u and w, is a subset or equal to R2, trivially. Okay, now conversely, to show that R2 is a subset or equal to span of u and w, take some arbitrary element, say z equal to pq of R2, where p and q are any real numbers, and show that we can always solve for alpha and beta such that z is equal to alpha times u plus beta times v. And what this would show is that z is a linear combination of u and v if we can always solve for alpha and beta. And if z is a linear combination of u and v, u and w, then that arbitrary vector z from R2 is an element of span of u and w. Okay, so how do we show that we can always solve for alpha and beta? Well, this is equivalent to solving this matrix equation all right, here's our z. We've just taken alpha times u plus beta times w and put that into a matrix product. And so can we always solve this matrix equation for alpha and beta? And the answer is yes, because this matrix here on the left is always invertible, or it is invertible. So we'll say since the determinant of that matrix is equal to 1 plus 1 equals 2, which is non-zero, A inverse, which is 1 over 2, 1, 1, minus 1, 1, this exists, and here it is. Okay, and so alpha beta is A inverse times PQ. And so yes, we can always find alpha and beta irrespective of the values of P and Q. So we've shown that R2 is a subset or equal to the span of U and W. Hence, these two have to be equal. And because span of U and W is span of UVW, span of UVW is equal to R2. Okay, so the answer to this question is yes, they do span R2, and this is why. Let's move on to question 2. Let P2 be the vector space consisting of all polynomials of degree less than or equal to 2. Let's write this out. It's the set of all a0 plus a1x plus a2x squared such that a0, a1, a2 are real numbers. Okay, so let f of x be equal to f0 plus f1x plus f2x squared and let's let g of x be equal to g0 plus g1x plus g2x squared. Now we can clearly see, since this requires 3 components, and let's say this specifically, since 1x and x squared is a basis for P2, and hence P2 has dimension 3, but we see here if we only have 2 vectors, f and g, then the span of f and g can have dimension 2 at most. So let's say that dimension of span f and G is less than or equal to 2, right? They could be multiples of one another, in which case it would be dimension 1. For example. Okay, and so we see then, hence, the span of f and g cannot be equal to P2. Okay, part B. So let W be equal to the span of f of x and g of x. Now note that the 0 vector is in W because we can say 0f plus 0g and get 0, the 0 polynomial, which is the 0 vector. So 0 is in W, and W is closed under addition, meaning that if I have an element of the span of f and g and another element in the span of f and g, and I add them those two together, then the result is in the span of f and g. So let's say, since if we have alpha 1 1 f plus alpha 1 2 g, right, as an element in the span, and we take another one, alpha 2 1 f plus alpha 2 2 g, then this is also in the span of f and g, because we can write this as alpha 1 1 plus alpha 2 1 times f of x plus alpha 1 2 plus alpha 2 2 times g of x, which is in the span of f and g, because this is a linear combination of f and g. Okay, also W is closed under scalar multiplication. So in other words, if alpha f plus beta g is in the span of f and g, then so is k times alpha f of x plus beta g of x. Okay, so hence W is a subspace of P2, and it's proper because it's not equal to, right? So I need a little bit more paper. Where should I write this? Let's put this on the side. Since W is not equal to P2, W is a proper subset of P2. So I put not equals under here. See that? Okay. All right, let's move on to the next page and next problem. Okay, so we have three vectors in 4 space. Show that they're linearly independent. All right, so we start off by saying suppose alpha u plus beta v plus gamma w is the zero vector. Okay, well, if that's the case, then we can write a matrix equation Okay, so we've got this, and then we can form the augmented matrix. But while we're at it, let's have a look at part C, because we can also do part C in our same row reduction. Okay, so thinking also about part C, let's form the matrix 1, minus 2, 3, 2, 1, 1, 0, 3, 1, 4, 1, minus 1. Then we'll put this. Then we'll put these two columns. And so what we're doing in adding these extra columns is we are looking at three separate systems of equations, and we can solve them all with the same row reduction. Okay, so let's get busy to row reduce this. Now I'm going to make everything in the first column divisible by 4 by multiplying by 4, by 2, not by anything, and by 1. Okay, so first row by 4, second row by 2, keep the third row the same for now, and the fourth row the same for now. Okay, now we want to replace row 2 with row 2 minus row 1. So 0, 10, minus 10, 0, 10, minus 20. Okay, good. Let's replace row 4 with row 4 minus row 1. Okay, great. I'll replace row 1 with row 1, the original row 1, so a quarter of row 1. And keep row 3 the same. Okay, now we can divide row 2 by 10 and multiply it by 2. In other words, divide it by 5. Keep the rest the same for now. Okay, and now I want to replace row 1 with the sum of row 1 and row 2. And then multiply row 2 by 3 over 2. In preparation for doing something with row 3. Okay, great. Now let's replace row 3 with row 3 minus row 2. And in preparation to deal with row 4, we'll multiply row 2 by 3. And we'll keep row 1 the same for now. Okay, continuing. Now we want to replace row 4 with row 2 minus row 4. We can see that we're going to get a row of zeros. Now let's replace row 2 with 1/9 of row 2. Keep row 1 the same. Okay, we have a row of zeros down the bottom because we can replace row 4 with row 4 minus row 3. And then let's replace row 3 with 1/4 of row 3. Okay, good. And now we can deal with the third column. And so let's replace row 1 with row 1 minus row 3. Let's replace row 2 with row 2 plus row 3. And we'll keep row 3 the same. And row 4 is a row of zeros. Okay, so this matrix is in row reduced echelon form. Now what does it say? Well, if we just ignore the last two columns, then this shows that alpha equals 0, beta equals 0, and gamma equals 0 in question A. And so UVW are linearly independent okay, but it says more. It says something about part C as well, which we'll come back to in a moment. Now I'm going to grab an extra piece of paper. You might need to also. So now let's answer part B. What is the dimension of span of UVW? Well, since they're linearly independent, the dimension of span UVW has to be 3. Okay, now for part C, let's interpret this. So we have P is equal to 3 times U minus W, and I get that from this fifth column of this row reduced echelon form, because that says alpha is 3 and beta is 0 and gamma is minus 1. So from the fifth column of the row reduced echelon form above. Okay, also Q is equal to, from the sixth column, minus U plus 2W in the sixth column of the row reduced echelon form of the above matrix. Okay, so what we see from these two that we got from this is that P and Q are elements of span UVW, and so span of P and Q has to be a subset or equal to span of UV and W. Okay, now also note P and Q are linearly independent because they are not multiples of one another. So PQ is a basis for the span of P and Q. Hence, span of P and Q is a two-dimensional subspace of span of U, V, and W. Okay, so that was a little bit of a tricky one. Let's move on to the next question. define a map from R3 to R2 by f of x, y, z is x plus 3y minus 2, comma, y plus z minus 2. Show that f is a function but not a linear map. Okay, so to show that it's a function, all we need to say is that it's well defined. So, since f is defined for all vectors x, y, z in R3, and with no ambiguity, f is a function. Okay, but it's not a linear map. Since if we just consider the third condition of a linear map, f of k times x, y, z is f of kx, ky, kz, which is, according to this rule, kx plus 3ky minus 2, ky plus kz minus 2. And this is not equal to k times f of x, y, z, which would be k times x plus 3y minus 2, y plus z minus 2, which would be kx plus 3ky minus 2k, ky plus kz minus 2. Right, so these are not equal, hence it's not a linear map. Okay, so that was an easy one. Let's move on to question 5. Consider the three vectors u, v, and w. Part A, show that w is a linear combination of u and v. Okay, so let alpha u plus beta v equal w, then 3, 1, 1 minus 2 times alpha beta is equal to 2, 4. Well, let's find the inverse of this matrix. So let A be equal to 3, 1, 1 minus 2. The determinant of A is minus 6 minus 1, which is minus 7. That's non-zero, so the inverse exists. Let's actually find it. 1 on minus 7, minus 2, minus 1, minus 1, 3. And so hence alpha beta is A inverse times 2, 4. So let's multiply this out. So we have minus 4 minus 4. Then down here we have minus 2 plus 12. So this gives us 8 on 7 and minus 10 on 7 for alpha and beta. So we've done part A. Now for part B, we have 8 over 7 u minus 10 over 7 v is equal to w. So we've written w as a linear combination of u and v now. Okay, next one says find real numbers alpha, beta, gamma such that alpha u plus beta v plus gamma w is the zero vector. So all we have to do is multiply this by 7 and take the result over the right hand side. 8u minus 10v minus 7w is the zero vector. So here alpha is 8, beta is minus 10, and gamma is minus 7. Okay, and we've done part C. So that was a fairly easy one. Let's move on to question 6. So I'll tell you straight away, there's a typo in this question in part C. It should be 5 to the power of n minus 1. So fix that. Okay, calculate the eigenvalues and eigenvectors of the matrix A. So let's calculate the trace of A. It's the sum of the diagonal elements, 2 plus 3, which is 5. Determinant of A is 2 times 3 is 6, minus the product of minus 6 and minus 1, just 6. So we have a 0 determinant. Characteristic equation is lambda squared minus the trace of A times lambda plus the determinant of A equals 0. So in other words, lambda squared minus 5 lambda equals 0. This factorizes as lambda times lambda minus 5. So let's let lambda 1 be equal to 5 and lambda 2 be equal to 0. So these are our eigenvalues of the matrix A. So now for the eigenvectors. So for x1, we consider the null space of the matrix A minus lambda 1 I. And so A minus lambda 1 I equals 2 minus 5 minus 6 minus 1, 3 minus 5. So minus 3 minus 6 minus 1 minus 2, and this is equivalent to 1, 2, 0, 0. That's the row reduced echelon form. Okay, and so from this we can read off an element of the null space of this matrix and call x1. Now what we do is we write these in reverse order, so 2 and put a minus on the other one. So 2 minus 1. Okay, now for x2, we consider the null space of A minus lambda 2I. But lambda 2 is 0, so A minus lambda 2I is just A in this case. This is row equivalent to 1 minus 3, 0, 0. And so the vector 3, 1, which we'll call x2, is in the null space of A minus lambda 2I. Okay, so we have our second eigenvector. So now for part B, we can diagonalize. A is equal to, now we concatenate x1 and x2. to form the matrix P. And then D is the matrix consisting of lambda 1, lambda 2 on the diagonals and 0 elsewhere. We have 5, 0, 0, 0. And then P inverse. Now what is the determinant of P? We have 2 plus 3 is 5, so 1/5. Swap the diagonal elements, put minus signs on the others. So this is P inverse. Okay, so here is our diagonal decomposition of A, and you can multiply this out and check that it gives you A. So now for part C, A to the power of n is equal to 2, 3, minus 1, 1, 5 to the n, 0, 0, 0, times 1/5, 1 minus 3, 1, 2. Okay, now we can pull out 5 to the power of n out of this and put it out in front. We can pull out the 1/5 in front of this and put it out in front also. So we see then that this is 5 to the power of n minus 1 times 2, 3, minus 1, 1, 1, 0, 0, 0, 1 minus 3, 1, 2. Okay, so it remains just to take this matrix product here. Now 2, 3 times this first column gives us 2. 2, 3 times second column gives us 0. Minus 1, 1 times first column gives us minus 1. Minus 1, 1 times second column of this gives us 0. Okay, so we multiply again. 2, 0 times 1, 1 gives us just 2. 2, 0 times minus 3, 2 gives us minus 6. Minus 1, 0 times 1, 1 gives us minus 1. And minus 1, 0 times minus 3, 2 gives us 3. And this is 5 to the n minus 1 times A, because this right here is A. Okay, so we're done with that question. Let's move on to question 7. Okay, so we've got a map from R3 to R4. Show that it's a linear map. So note, we have f of x, y, z is equal to a x, y, z, where A is the matrix 3, 7, 1, 4, 8, 2, minus 3, minus 9, 0, 1, 1, 1. Okay, so just from this, because it's matrix multiplication, this means that it's a linear map, and this is a result of one of the previous theorems. Okay, so now for the image, so part B, image of F is equal to the column space of A, which we can find by row reducing the matrix A. And so A is equal to 3, 7, 1, 4, 8, 2, minus 3, minus 9, 0, 1, 1, 1. Okay, now replacing row 3 with the sum of row 3 and row 1, we have 0, minus 2, 1. Now let's multiply row 4 by 3 in preparation for what follows. Which is to replace row 4 with row 1 minus row 4. We'll replace row 3 with 2 times row 3. Now let's replace row 2 with 3 times row 2. And we'll replace row 1 with 4 times row 1. Okay, next we'll replace row 2 with row 1 minus row 2. And we'll replace row 1 with a quarter row 1. We can see that all rows 2, 3, and 4 are identical. So we're going to get 2 rows of zeros. Okay, next let's replace row 2 with a quarter row 2. Or no, let's go a half row 2 times 7. So 0, 14, minus 7. And then we'll replace row 1 with twice row 1. So 6, 14, and 2. Now row 1 will go to row 1 minus row 2, so 6, 0, 9, and we'll replace row 2 with 1/7 of row 2. Okay, so now we have almost the row reduced echelon form. So it remains to just divide or multiply row 1 by 1/6 of row 1. So 1, 0, 3 over 2. Multiply row 2 with 1/2 of row 2. Okay, and so the last matrix here is in row reduced echelon form. Okay, so now for the interpretation, where are our pivots? The pivots are in columns 1 and 2. So we extract columns 1 and 2 of the original matrix A, and then we say that the image of F is equal to the span of those columns. So 3, 4 minus 3, 1, and 7, 8 minus 9, 1. Okay, and so then we get a basis for the image. All right, so now let's do the kernel. And note this has dimension 2. So the rank of F is equal to 2. So by the rank plus nullity theorem, we expect that the dimension of the kernel is equal to 1. So that 2 plus 1 is equal to that 3 up here, the dimension of the domain of F. Okay, now for So this here is part B. So for part C, the kernel of F is the null space of the matrix A. So if XYZ is an element of the null space of A, then what we have is it's row reduced echelon form times XYZ equals 0 also. And so we can multiply this out and get x plus 3 over 2z is 0, y minus 1 over 2z is 0. And rearrange this and get x is equal to minus 3 over 2z, y is equal to 1/2 z, and of course z is equal to z. Hence, we can use z as our parameter and then even multiply that by 2. So minus 3, 1, 2 is a basis for the kernel of F. And notice it has dimension 1. So nullity of F is 1. 2 plus 1 is 3, which is a nice little check. Okay, let's move on to question 8. The trace of a complex number is the sum of the conjugates. The norm of a complex number is the product of the conjugates. So let's have a look at this. So the imaginary parts vanish. We have 2a. Excuse me. The trace of a plus bi is 2a, and the norm of a plus bi is a squared plus b squared. So f of a plus bi is equal to 2a comma a squared plus b squared. And so this is not a linear map. Since it fails the third condition to be a linear map. This is usually the easiest one to check to show that something is not a linear map. Okay, so this would say that we have 2 times ka, comma, and then take this and square them. So k squared a squared plus k squared b squared. Okay, on the other hand, k times f of a plus bi is k times 2a a squared plus b squared, which is 2ka k a squared plus k b squared. All right, and these two are not necessarily the same. They're not the same in general. Okay, so F is not a linear map. Okay, now for part B. So this is the real part. This is the imaginary part. So I'll write RE and IM for these. Okay, so let's have a look at what this is. So G of A plus BI is equal to the real part of A plus BI plus the imaginary part of A plus BI. And so the real part of this is A, the imaginary part is B, so this is A plus B. Okay, so G of the complex number A plus BI is just A plus B. So we've got to show that this is a linear map. Okay, so first note that C and R are vector spaces. Okay, now let's do the additive property. So G of Z1 plus Z2 is equal to G of A1 plus B1I plus A2 plus B2I, which is A1 plus A2 plus B1 plus B2. And so this is equal to G of Z1 plus G of Z2, which would be A1 plus B1 plus A2 plus B2. Okay, so now for the scalar multiplication property, G of K times Z is G of Ka plus Kbi, which is Ka plus Kb, which is K times A plus B, and that's K times G of A plus Bi. Okay, so G is a linear map. Alright, so now for the image and the kernel. So image of G, what comes out of this map? Well, it would be the set of all real numbers. In other words, the map G is surjective because every element of the real numbers came from somewhere. So since G of A plus 0i is equal to A, so if I took an arbitrary element of the real numbers A, then this is the element of the complex numbers that it came from. So it's surjective. Or onto is another word for surjective. Okay, so then the image of G is equal to the span of just 1. Okay, so 1 is a basis for the image of G. Now for the kernel, suppose that G of A plus Bi is equal to 0. Well then A plus B equals 0, so B equals minus A. I think I need to grab some more paper here. Hence, the kernel of G is span of the vector 1 minus I. In other words, any multiple of 1 minus I will get sent to 0 under the map. So A minus AI, which is an arbitrary multiple of 1 minus I, so G of this is equal to A minus A, which is 0. Okay, and so to answer the question, this vector 1 is a basis for the image of G, and 1 minus I is a basis for the kernel of G. Now let's count their dimension. So the rank of G is equal to 1, and the nullity of G is equal to 1. And notice that the rank G plus the nullity of G is equal to 1 plus 1, which is 2, and that is the dimension of the domain C as a vector space over the real numbers. Okay, because C is equal to the span of one comma I, and this is two-dimensional over the real numbers. We have two of these vectors there. All right.